Myself, Dr. Babu. Currently, I was working as an assistant professor in the Department of Electrical and Electronics Engineering at the University of Surampalem. Today, we are going to discuss about the unit in Electrical and Network Analysis 2. The title is Transients in DC Circuits. So, coming to this outcome, we are going to analyze the transient behavior of electrical networks for DC excitation. Our network elements such as resistance, inductance and capacitance, we are going to study these responses with the help of DC excitation in this unit. Okay. It contains transient response of RL, RC and RLC circuits for DC excitation, and also we are going to find the solutions of current or voltage with the help of differential equations method and Laplace transform method. So, we are going to study both the methods. Okay. If you look into the figure carefully, before a fault or supply, that means before a fault and after fault, like that we can study, or else all of a sudden transient is applied. Transient in the sense a sudden change during Diwalis or during fault current, during suddenly increasing the load condition. That means we are suddenly switching on the loads, unnecessary loads. Not only unnecessary means, suppose if it is in a fault condition kind of thing, more amount of power is required, or else during functions suddenly large amount of power is required. Especially during summer season, water quantity in the reservoirs will be very less, even though our electricity board has to supply the electricity. So, in order to do this, there is a switching of the supply in for areas. So, in order to do this, they will supplying the power efficiently. But with the less amount of water in the reservoir, if they need to supply more power than generated power, it leads to transients. So, now we are going to study the transients in the DC networks. This unit completely deals with transients in DC, and in the upcoming unit it deals with transient responses in AC circuit. Suppose here if you look into the figure, means this diagrams, see here 0 to 2 seconds, 0 to 0.2 seconds. During this interval of time, our output voltage is 0. That means this state is called steady state. Okay. From 0.2 to 2 seconds, this period, you can see that the current is exponentially increased. That means at a high rate, exponential manner, all of shunt is increasing. In between 0.2 to 2 seconds, our voltage has been increased from 0 to 1 volts. That means an abrupt change in voltage has been takes. This period is known as transient period. Okay. This period is known as transient period. After the transient period, again the system will be in stable condition. That means we are forcing our system to be in stable condition. This is also called as stable or steady state condition. Okay. Even in this figure also, from 0 to 0.2, our system is in stable, and when it is greater than, when it lies between 0.2 to 2 seconds, this state is called as transient period. As I have stated earlier, this state is known transient period. When it is greater than 2 seconds, this state is known as steady state. Okay. So, in a response, you will be getting this steady state as well as a transient condition. That means a total signal is given by steady state plus transient response. Okay. We will be calculating all these values in the further. Okay. As I told you earlier, the network elements are resistance, inductance, capacitance. Now, during abrupt change conditions, during abrupt load or abrupt power disturbance conditions, we are going to study the values of resistance, inductance and capacitance, and also the combination of all the three. That means any two, like RL, RC and LC we are not studying, but RLC we are studying it. Okay. So, the combinations of RL, RC and RLC we are studying with the help of these transient states. Okay. During this mode, during this DC transient mode, the supply is DC supply. Okay. As I was told earlier, the total response of the circuit is given by forced response plus transient response. That means forced response is nothing but our steady state condition, whereas transient response means the response that is during the transient period. That means the response that you have calculated during this transient period is known as transient response, and during the steady state condition is known as forced response. Okay, see. Next one. For these transient conditions, we can obtain the equations with the help of integral differential equations. That means integral on differential d by dt equations. With the help of these two methods, we can get the solutions for it. And also, these two solutions can be applied with the help of classical method and Laplace method. Classical method in the sense a differential equation method. Okay, classical method in the sense differential equation method and Laplace method. Coming to the classical method, in classical method, there will be again you will be getting two types of solutions. First one is complementary solution and the next one is particular solution. Okay, that means complementary solution in the sense it represents the natural response. Okay, that means before applying boundary conditions. Okay, that in the sense for this it is having zero boundary conditions, and in the particular solution we are going to apply initial conditions or boundary conditions. That means initial conditions in the sense I of 0 plus or I of 0 minus or V of 0 plus or V of 0 minus. That means V of 0 plus and V of 0 minus are for capacitance. Whenever capacitance is there in the circuit, the initial conditions will be V of 0 plus and V of 0 minus. Whenever inductor is there in the circuit, the initial conditions are I of 0 plus and I of 0 minus. So, with the help of this, we are going to attain the solutions for classical method, is differential equation method. Okay. Hope it is clear. Again, I am repeating it once. Listen carefully. In differential equation method, we are going to find the solution with in two parts. First term is known as complementary function part and the second term is known as particular solution part. In complementary equation part, boundary conditions are not applied. Directly by writing KVL equations, we can find it. But whereas in particular solution, we are supposed to apply the boundary condition, that is I of 0 plus and I of 0 minus or V of 0 plus or V of 0 minus. V stands for capacitance and I stands for inductance. The major reason is inductor does not allow sudden change in currents, whereas capacitor does not allow sudden change in voltage. So, that is why for inductor you will be giving current I of 0 plus is equal to I of 0 minus, and whereas for capacitance V of 0 plus is equal to V of 0 minus. These two are the initial conditions. And coming to the Laplace transform method, this method is very more superior and very much easy over the differential equation method. Okay. Here in this method, we no need to apply the initial conditions. This is the major advantage of it. Now, we are going to see the both RL and RC and RLC circuits with the help of this both classical method and also the Laplace transform method. In the same text, we will be going to see numerical also. Okay. In the previous case, I have told you that I of 0 plus or I of 0 minus or V of 0 plus or V of 0 minus. Here this 0 plus or 0 minus stands for time period. That means this t is either 0 plus or 0 minus. Okay. Suppose if t is equal to 0 plus in the sense just immediately after closing the switch. If t equal to 0 minus in the sense the time at which the switch is just before closing the switch. So, if you observe, this means these initial conditions, these mainly depend upon the past history. Okay. One is past history, that is t equal to 0 minus, that means just before closing the switch. The value of voltage or current just before closing the switch, how it will be, we are going to study. And also the second condition is immediately after closing the switch, that means t equal to 0 plus. Okay. Here see the values of capacitor voltage and inductor current references t equal to 0 minus should be calculated. Okay. And at the same time t equal to 0 plus should be calculated. That means if you are going to study RL circuit, L in the sense inductor will be there. So, I will be going for I of 0 plus is equal to I of 0 minus condition. If I am going for RC circuit, their capacitance will be there. So, I will be going for V of 0 plus is equal to V of 0 minus. So, that means before closing the switch and after closing the switch, either the voltage values or current values will remain same, depends upon the resistance, depends upon the inductance or capacitance in a circuit. Okay. Here you can see the switching time instant. Here this is the time period, this is plus infinity condition and this is minus infinity condition. Okay. This is t equal to 0 minus and this is t equal to 0 plus. Okay. You can see it, see here. For t equal to 0 minus in the sense, the time ranges between 0 minus infinity to 0. Okay. If t equal to 0 means in the sense the time range between minus infinity to minus 0, and t equal to 0 in the sense just at an instant the time t equal to 0. This is known as initial value. Getting my point? If t equal to 0 minus in the sense you need to take the time values in between 0 minus infinity to 0. When t equal to 0 plus in the sense you need to take t equal to 0 value. The reason is just at an instant the time equal to 0. And the third condition on t equal to infinity, that means in this case t equal to infinity in the sense take the time values in between 0 plus to infinity, and this is known as final value. Okay. Here total 3 guys will be there. 0 minus in the sense minus infinity to 0. T equal to 0 plus means t equal to 0, and this is case is known as initial value. And t equal to infinity in the sense the values ranges from 0 plus to infinity, and this is known as final step, final value. Okay. Next, moving on to initial conditions in network elements. So here I have considered a simple R circuit which is connected in series with voltage, and here I have connected a switch S. Okay. When time t equal to 0, the switch will be closed. As I told earlier, this is resistor. Okay. The resistor is purely a resistive element. Okay. It is not an inductor or capacitor. So as it is a purely resistive element, it does not exhibit any transient response. Okay. Its operation will remain same in transient response and as well as normal circuit also. So this R resistance does not exhibit any transient response like inductor and capacitor. Therefore, at t equal to 0 plus or t equal to 0 minus, okay, I is given by V equal to R. Okay. At t equal to 0 minus, that at t equal to 0 minus, that is before closing of switch, the current flowing through resistor is I, which is nothing but that is equal to 0. Okay. At time t equal to 0 plus in the sense, that means immediately after closing the switch. Okay. Then the current I is given by I is equal to V by R. Okay. So before closing the switch, the current flowing to the resistor is 0, and after closing the switch, the current flowing to the resistor is I is equal to V by R. Now we will move on to inductor. Okay. As I told earlier, this inductor does not allow any sudden change in current. Okay. And also inductor is given by Z is equal to XL. XL in the sense omega L. Omega L in the sense 2 pi F into L. In DC, the inductor value F in DC the inductor frequency is 0. That means the value of inductance will be 0 ohm. Okay. But depending upon its condition, it contains some internal resistance. So we will be calculating that part also. We will be considering that part. So now see, at time t equal to 0 minus, at time t equal to 0 minus, the inductor will behave as a open circuit condition. The reason is, at time t equal to 0, we need to consider the values of in between minus infinity to 0. Okay, as I stated earlier, at time t equal to 0 minus, we need to consider the values between minus infinity to 0. So if I consider the value of inductor will be minus infinity, that means the inductor will completely behaves like an open circuit. Okay. Now coming to t equal to 0 plus, that instant switch is closed, some amount of current will be flowing through it. But as per the initial value condition for inductor, IL of 0 plus is equal to IL of 0 minus. Okay. IL of 0 plus is equal to IL of 0 minus. So if I write the KVL, okay, let me. 0 plus is equal to 0 minus. So if I write a KVL equation for this, the equation will be V is equal to L into di by dt, where L is inductance and di by dt is the differentiation with respect to time. Okay. Now see, when time t equal to infinity, the inductor when time t equal to infinity, it behaves like short circuit. Okay. During this course, the values across the inductor IL is equal to 0 plus, and that means before and after course this, the inductor value will be V is equal to L into di by dt. Now coming to the capacitance value, it is also similar to similar to inductor, but in capacitance, okay, when time t equal to 0 plus, it should be the capacitance value is replaced by some initial voltage V naught, okay, initial voltage V naught, and during this time the capacitor will behave like a short circuit. So during this period we see if it is a capacitance, as I told earlier, the voltage across capacitance will be Vc of 0 plus is equal to Vc of 0 minus. So that means it is showing some, when time t equal to 0 plus, the capacitance value will be charged and will store some value, and this V naught will be released and it is passed through the circuit. When the switch t is equal to 0 minus, the capacitance will be, the switch will be in open condition. During this case, this capacitance will be having some initial voltage of V. Therefore, the current flowing through the capacitance I is equal to C into dV by dt. Okay, that means before closing the switch, the current value may be 0, but after closing the switch, it contains some particular value of current. Due to this, internal voltage will be arising, and the equation is given by I is equal to C into dV by dt. Now let us look into this the values of RLC in its equivalent form. So as I told earlier, when time t equal to 0 plus and t equal to plus infinity, the resistor will behave like t equal to infinity in the sense t equal to 0 minus. Okay. When time t equal to 0 plus t equal to infinity, the resistance will behave as it is. Okay. And also stated that for inductor, okay, at time t equal to 0 plus, the inductor will behave like an open circuit. During this time, the capacitor will behave like short circuit. Whereas when time t equal to infinity, opposite case will be existing. See here. During this period, the inductor will be short circuit and the capacitance will be open circuit. The reason is here the time period is t equal to infinity. In a similar manner, under some initial conditions when current I naught is flowing through the inductor, it is represented by a current source in series with circuit. Whereas at time t equal to infinity, it is represented by current voltage source in parallel with the circuit. That means here short circuit will be there. In a similar sense, for capacitor with initial voltage of V naught, it is directly represented with a voltage source of V naught at t equal to 0 plus. Whereas when t equal to infinity, it is represented by voltage source with plus or minus V naught with open circuit condition. So these things we need to remember, even though we didn't remember also, but we can draw and solve the equations. Okay, we will look into this. Coming to its summary, okay, when time t equal to 0 plus, the inductor will behave like an open circuit and capacitor will act as a short circuit and resistor will remain same. Okay, and when time t equal to infinity, the inductor will act as short circuit and the capacitor will act as open circuit. This you can observe this from this table, okay, from this diagram. And next one is the initial conditions. The initial conditions are, for inductor it will be I of 0 plus is equal to I of 0 minus. That means the current before and after closing switch should be equal. Whereas for the this is for inductor, INDUCTOR. Whereas for capacitance, V of 0 plus is equal to V of 0 minus. These are the initial conditions. Okay. Next one. In this slide, we will be going to see the procedure for solving the initial conditions. Okay. In order to solve the initial conditions, we should go with t equal to 0 plus condition at first. Okay. When time t equal to 0 plus, that means the instant at which the switch is closed. Okay. At that moment, the inductors will behave like open circuit. Okay. And the capacitors will behave like short circuit. During that time period, you need to calculate the values of current I naught, and if any voltage sources are there, you need to calculate the values of voltage V naught. Okay. During step 2, we need to find the differential voltages of current, differential values of current and differential values of voltage. This with the help of this KVL and KCL equations and substituting the values of I and V at t equal to 0 plus, we can get it. So these procedures, if you are going to solve a numerical means, then you will get an idea. Okay, with this we are going to conclude our session. Thank you.